similar kind of method. So we are going to start with designing our own large language model. It will be a class which a lot of people, if you know coding about, it will be a little easy. If you don't know coding as well, I will try to explain the code that we are going to write in very simple or simplistic way. There is a little bit of maths involved in this, and this will be the only coding class that we will have in our master classes, the 3 master classes, just to get you a gist of how can we create a large language model for ourselves as well. So let's say that you want to create a large language model, what can be the approach? So this will help you also in understanding the large language model little bit more. And what we explored in the last class about the transformer architecture, this is kind of like um, a practical implementation of the same. So before we move ahead, I just want you to raise hand if you are comfortable or have coded any time before in Python. If you have not, then that's fine. It's also okay. So I'm saying that seeing 22 participants, more than 30 participants have now raised hand. There are 367. Once we have kind of like a healthy amount, maybe I can go with that understanding and can go and dive deeper into Python. And then otherwise, if we have like less people, those who know Python, maybe we can go with less more intuition rather than Python. I can see that a lot of people are raising hands. They know Python already. If you have ever coded even a single code in Python, maybe yeah, that's also fine with me. All right, thank you so much for being participative and raising the hand. Still waiting for other participants. So I think that most of the people here know Python and they have coded on Python. So we'll be using Google Colab, and I hope that you have used Google Colab before. I'm not using VS Code because of the dependencies. That means that you don't have to like install the libraries. They already are in Google Colab, so we will be using that. All right, so I am seeing some messages like Python is suitable. Thank you so much for replying that we can go ahead with Python. Okay, so I will share my slides and start building the large language model from scratch. Okay, so some people are messaging that they know C, C++, Java, Python for sure. Thank you so much for letting me know so that I can dive into Python. So maybe I am comfortable with the code as well. Okay, cool. So I'm sharing my screen with you where I have designed this PowerPoint presentation. So then we will have kind of like a framework in which we will work. So the framework is already designed by me. You can use that framework to make your task easier. All right, so let me quickly share my screen. Uh, okay. All right, hello and welcome to this masterclass of creating large language model from scratch. Last masterclass, I got a feedback that I speak too fast. So if I'm speaking anytime too fast, because sometimes I tend to kind of like think fast and then speak fast. So maybe just let me know in the comment boxes that I'm not able to understand what you are saying. Maybe you can slow down a bit. That would be helpful for the other guys as well. All right, so let's start creating tiny language model from scratch. Maybe we will not be able to create a large language model because of the GPUs that we have. Um, if you remember about the last lecture, in the last lecture we learned that for creating a large language model we need a lot of GPUs, right? So of our computers, they don't have these GPUs. So we will not be able to create a large language model, but maybe we will be able to create a tiny language model. Okay, so but the idea is to create a language model so that it can write or it can generate text. All right, so let's begin with creating a large language model from scratch. So this is the introduction to the product or project which we are building today. So we are building a product of on Mahabharata. so this model will be a tiny language model built on Mahabharata text. Okay, so Mahabharata. So this is kind of like a user interface that I have created of the output that I have got from the model. Okay, so although this is not legible, like this is not a very desirable output because I can't understand what is written in here. But the idea is to generate these words from scratch by training our model from scratch so that it has some understanding of the language, right? So like it can write Brahmanas, it can write crow, it can write uh, something like this, like after then of the three then that himself it, right? So right now it is not a perfect model. We cannot use this for production, but the idea is to kind of like design this from scratch the way that ChatGPT has designed this, so that we learn how to even design a large language model. If we get a job in let's say a big LLM company, then we know the ins and outs of creating a large language model. So right now here, my model, what it does is when I click on generate text, it generates a random text like Mahabharata. So when you copy this text and paste it on, let's say Google, so Google will tell you that it is something similar to what Mahabharata is, right? So the idea is to design a text generating model, so generative AI model for text. Okay, so what we will build a tiny language model. We will train it on Mahabharata text. Okay, so why I'm choosing Mahabharata? Because Mahabharata is a long epic, and no other reasons to choose Mahabharata apart from it being a text which is very long, and it also has some structure, right? So if you see Mahabharata, it is not written like a story. It is written like some paragraphs, right? So it is written like a verse form. So it has like some so if I show you the corpus of Mahabharata, so it is like this, right? So chapter 1, Dhritarashtra ranged thus for the battle on the sacred plain on Kurukshetra, says Sanjaya, say what wrought my people and the Pandavas. So it's written like in a poem form. So we are going to train our our model on this poetry form of text like Mahabharata, and we are training it so that it can generate something like this. Maybe it will not make any sense because of the GPUs, but if we have a larger corpus, if we can take all the text that is in the world, maybe we are able to um, generate this text which makes more sense, right? So it will only be a matter of scale after this. So if you see, this is the text that we are going to use. I have a link to the text that I have. So I will paste this link on the um, in the chat so that you can go to this and download this from there. But you don't need to download it because I already have the code to download this. Right. So if you see the corpus, so if you see the last lecture, we started with designing our own corpus, right? So the corpus can be designed by going into the all the websites that are there in the world, and we crawl these websites using web crawlers, and we download this text from the website, right? So to build a corpus, you need to use common crawl, which crawls 250 billion pages. It's 1 picobillion of data, which is greater than 1 million GBs of data, right? So you take in all the data that is there in the world and you train it. But right now we don't have all the data. We cannot do that because of the memory capacity as well. And also, we are not creating something like a large language model. We will not be able to create with the GPUs that we have, but we will be able to create a tiny language model based on Mahabharata. Okay. The second step is to extracting this text from HTML. So text extraction is difficult because if you kind of like crawl on the internet, you will see the data like this. So it will have these HTML code as well. It has all these script tags as well. So the idea is to filter this out. So we will filter all of this out after we crawl on a website and only take the relevant text. So here the relevant text is one of the best and most rewarding features of training material or whatever is there, right? So we only take the relevant text and we eliminate the links, the code. So we filter it out to train our model. We also need to remove the harmful content and personal information from our model because we don't want it to spit harmful content, right? So if you go to ChatGPT and ask it how to design a bomb, maybe it will not tell you how to design a bomb because of the harmful content. We have fine-tuned it to remove that harmful content, right? So once you build a large language model, you also need to know how you are training it on the data with, right? The data that you will train it with, the learning it will get from that data. So you need to remove that content also. Also, you need to remove duplicate URL, document, and lines. So there are these duplicate URLs here, which are there in the data. You can see that this is smartcode.com. So you need to kind of like filter it out. And you also need to remove low quality content using heuristics and models. And finally, you want to mix the data also. So let's say that you want to build a large language model which is good in code. So maybe you will train it more on the code data and less on, let's say, stories and articles. Like if you talk about Claude, then Claude is very good at code, and GPT is very good in generating poems and journal articles, right? So you want to decide which way do you want to go. So if you want your model to be good at code, maybe you will train it with more code data. You will mix more code data into it. If you want it to be better at, um, let's say storytelling, then maybe we will put in more emphasis on storytelling data. Being said that, I already have curated the data for you. So I have done all these steps. So I have downloaded it from internet, the Mahabharata text. I have done the text extraction and made it in a .txt format. I have done the content filtering and removing the harmful content. I have also removed the duplicates from this. I have also done quality filtering. And this I have not done because I am training it on Mahabharata. So I am not mixing any data, right? So I already have the data with me. I will paste the link to this Google Colab file in the chat box so that you all can go to this. In this Colab file, we have all the steps required to make our own large language model. I will explain you steps one by one, and we will be having our own large language model by the end of this session, right? So although that will be a tiny language model that will not speak very perfectly, but still that will be something that can generate some text. Okay. So maybe my Zoom kind of like is not working properly. Okay. Hmm. Okay, so you don't need to use VS Code from this. You can use the you can use the collab, right? So I am giving you the collab link. Okay. Okay, if someone asks us how we created corpus, you say that you took the corpus from the Project Gutenberg, right? So the source was Project Gutenberg Mahabharata text, and you crawled Project Gutenberg, and you kind of like downloaded the text from there and converted it into a text file. Okay, so one user was asking, how can we describe how did we make the corpus, right? So right now we are just doing it from Project Gutenberg Mahabharata text that is available. I am pasting this link of the collab file so that you can download the text, right? So I already have the code there for loading the corpus, so you don't need to do this. So I will just paste the code here. Let me get the access to my code. In the chat for everyone. Okay, I have pasted the link to the uh, collab file. So you can go to the collab file and take the link from there. Okay. So if you open the collab file, if you press Control and go to the collab file, you will see my collab file like this. So I'm sharing my desktop. Okay, I have pasted the link. So all right, so you can take in from this. So I have pasted the link again in the group. I'm pasting it again so that everyone can get that. And you can go to the collab link and you will see the file already there. So there are some things in the file which I have already done. So first step is to loading the corpus. So this is the function wget, so that you will get it from my GitHub repo. So once you kind of like run this code, uh, okay, so first thing that you need to do is you need to make a copy of this, because this is not a editable Colab notebook. So you'll need to make a copy and name that copy as your own name, right? So you say here you can name it like Amit. So instead of copy of, you can name like with your name. So I'm naming it with my name, Amit Mahabharata, tiny LM IPYNB. Okay. So now step one is to load the corpus, and you will just run this code and load the corpus. And this is what I already have given, because this is what you don't need to kind of like code on. So it will connect you to the runtime. And if when it loads, you will see it here in your files. Okay, so this will get this from my GitHub repo. And from there, it will load that file here in the files. So once you run this, this Mahabharata.txt will be there. And then reading the file from the system is very easy. You use the with open function. So with open, you are opening Mahabharata.txt and you are opening it raw, right? So for R, it is for opening it as raw files. Encoding you are using is at UTF-8 encoding. And you are making text which is kind of like a string by using the read function. So everything that is there in Mahabharata.txt, you are putting it into this text string. Okay, so by this read function, so the text will contain um, these all the text that is there in this. So if you print the length of data set in the characters, you just use this len function. So len function with text, you will see that it has 13 lakh 34,646 characters in my whole Mahabharata.txt file. So you run this, and by running this, you are opening this Mahabharata.txt in raw format, and you are putting those characters in a text string. And if you print the length of this string, you will see that there are 13 lakh characters in this. Okay, and if you print the first 1,000 characters, then the first 1,000 characters will look like this. The Mahabharata Adi Parva, section 1. Om, having bowed down to Narayana, and Nara, the most exalted male being, and also to Goddess Saraswati, must the word Jaya be uttered. Then it starts from this Ugrasrava, the son of Lomharshana, surnamed Swati, well versed in the Puranas, bending with humility, one day approached the great sages of rigid vows. So for these are the first 1,000 characters of Mahabharata, right? So if you run this, you already have now the Mahabharata text as your corpus. So your corpus is this text, and now uh, um, we will do all the steps that are required in order to create this language model. And we have like 6 steps that we need to do in order to create our large language model. Okay. So step one is tokenization, which we already have mentioned, that we need to chunk the words into sentences, chunk the sentences or the text into sentences, words, and characters in order to tokenize, in order for the computer to learn them, right? So computer does not understand this. Computer has no meaning for this. It only understands numbers. So we need to kind of like somehow make or convert this text into numbers so that computer can work with those numbers. Okay. So we will do step by step everything. Okay. You don't need to change the runtime to TPU. It's okay. It can run in CPU as well. So it's not a very big code. Okay. So because we are creating it from scratch, and our corpus only have 13 lakh characters. So we don't need TPUs for that. Okay. So now if you are ready with this, just give me a thumbs up, like maybe just raise a hand or give me a thumbs up so that we can move ahead. If you want to give a thumbs up in the chat, you can also do that. Or if you want to just raise a hand, you can also raise a hand. Thank you so much, Pallavi, has also done this with the step. That means that you have copied the Colab file and you have also downloaded the corpus and you are ready to train the first large language model. Thank you so much, Ashish, for saying move on. Mohit is also there. Simran, Angshita, thank you so much. Renuka also. Um, um, Tanvani Anjali also, thank you so much. Anjali Tanvani. Parth, okay, cool. Meet. Thank you so much. Okay, so we are now moving ahead with our second step. Okay, so we have now our corpus, right? So our corpus is loaded. So what we have done so far, we have downloaded our corpus, and if you see here, your corpus will be downloaded like this, right? So you can also look at your corpus by maybe double clicking this, and you will see that your corpus is here. And we have also read it, we have opened it, and we have also printed the length of data set. And we also have printed the first 1,000 words of this data set. Okay, now um, step 3 is tokenization, right? In the last section, in the last class, we talked about tokenization. We said that we want to convert the sentences or our text into chunks. Why? Because computer does not understand words. They only understand tokens. Right? They only understand numbers. So we need to somehow convert these words into numbers. Okay. So before converting, we are going to check how many unique characters are there. Okay, so in my model, because of the GPUs that because I don't have access to GPUs, and maybe we are not building a cluster of GPUs, we are only using the available um, compute power that we have that Google Colab gives, right? So what we will do is we will make a character level tokenizer. That means that I am chunking all of these characters out from my context, from my content. Okay, so I'm chunking it character by character. So chunking it THE, then space, then MAHABHARATA. So the idea is to learn how two different characters come together to form a word. Okay, so the idea or the thing that I am trying to achieve from this is to learn how these words are formed. So some meaning of these words I am trying to understand, and my model will be able to generate these words, and something like Mahabharata will be produced. Okay, so I'm going to check first how many unique characters are there. So I'm using a character level tokenizer. There can be many ways of tokenizing, and I will show you what are the different ways of tokenizing. Tick, there is tick tokenizer, uh, nicer from Vercel. So they have created this tick tokenizer, which tells what kind of content, how they chunk the content into. All right. So let's say I have this content. How different language model they tokenize different content. Okay, so if I take GPT-4o for that example, GPT-4o chunks this as the as one token, then ma as one token, h as one token, ab as one token, har as one token, ata as one token. So they have designed their own tokenizer, and for each token they have some value here, right? So for the they have value 27022. For MA, they have value 12615, and this MA also includes that dot. For HAH, they have value 39. For AB, they have value 2912. So they are converting this whole sentences into chunks, and they are giving some value to these chunks. Okay, so this is what tokenization is. There are some other tokenizers that you can also try from there. Maybe you can have GPT-2 as tokenizer and paste it here, and you see that there are 58 tokens, similar to how it is in GPT-4. But then again, each token has different meaning here. You can also check for text embedding 3 small. What are the tokens for this text, and it will just show you those tokens. Okay, so I'm just showing how tokenization is done by different models. Maybe GPT 3.5 tokenization. Again, looks like this. So I need to convert my words into numbers, right? So right now I am not working on word level. I am working on character level. Okay, so I am first going to look out how many characters are there, and I'm going to sort these list of characters, right? So I'm going to what I'm doing is basically I am making a sorted list of all the characters that are there in my text. So this set function will take in all the characters that are there in my text, all them unique one, and this list function will make a list of all the characters that are there in my text, and this sorted one will sort them from alphabetically, right? My vocab size will be the length of my characters. Okay, so vocabulary size is always the length of tokens. So if I divide my whole Mahabharata into words, so my vocabulary size will be the number of words that are there in my Mahabharata, unique words. Okay. So my vocab size here is length of the characters. Why? Because how many characters or unique characters that I have. So I am doing a character level tokenizer here, not word level. You can try word level tokenization as well, but it will give you very different results. Right now, we want it to also learn how Mahabharata is written, right? It's written in poem form. It's not like written in words. And there are some unique words also that are written in poems, which are not very popular in English language. So that's why I'm not using word level tokenization. And if you print and join all these characters, you will see that how many characters are there in the tokenizer. And if you print the vocab size, then you will be seeing that 75 should be the answer of this. So in my text, there are 75 different unique tokens. Okay. So quickly do this code by in 3.1. So what you need to do is you need to go to this section 3.1, and you need to add a code block in here, and you need to write this code here to check how many characters are there, as how many unique characters are there, so that we can create our own tokenizer for this. So every company, it creates their own tokenizer for themselves to train their large language model. Okay, so Sarvam AI also has done one thing very, very great is their tokenizer is amazing. So they faced a problem that Sanskrit was not a better the generative AI models that we had were not good at Sanskrit. So they created a tokenizer that could tokenize Sanskrit in a very, very easy way. So that's what different that they did. And that's why their model is more unique, right? So this is what we are also doing. We are creating our own tokenizer. Okay. Okay. So if you have done this, maybe you can just give a thumbs up again, and maybe we can move ahead with our code. Thank you, Anjali. Thank you, Takarshi. Thank you, Tanishka and Anurag. Okay. So we are ready for the second part. So we have made our tokenizer, and you see that 75 unique characters are there in our whole whole code. Okay. So in our whole corpus. So now what we do is after we have known how many characters are there, we will create our tokenizer. Okay. So how will you create a basic character level tokenizer? So the idea, very basic character level tokenizer. So if I have shown you this tick tokenizer, so it is giving some value to these tokens, right? So a very basic character level tokenizer, how will it look like if I can give a value to each character, right? So if I say A is, let's say, some integer 1, okay, and B is a integer 2, right? So I am changing my characters to tokens which have some numerical value, right? So 1, 2, so maybe C, I give it a value 3. Okay, so I will create a encoder or a tokenizer which will encode all my characters into numbers. Okay, so this is encoder. And I will create a decoder also. that will convert my numbers back to my words. Okay, so 1 will be converted back to A, and B will be converted back to B. Sorry, 2 will be converted to B, and 3 will be converted to C. Okay, so every tokenizer has an encoder and a decoder, right? So encoder, what it does is it converts the words or characters into numbers, and a decoder converts the characters back into words or characters. Okay, numbers into characters. So we are converting words into numbers in encoding and numbers into words in decoding. Okay. So how will we create a basic character level tokenizer? So the strategy is this, that we give an integer to each character, and what we need to do is we need to create an encoder that converts each unique character to an integer, and then we create a decoder that convert each integer back to a character. Okay. So this is the code for this. So I am using a function called string to integer. Okay, so this string to integer, what it is doing, that it is creating a mapping from each character, so character to integer. So it is creating a mapping from character to integer. For I, which is integer, comma character, I am going to enumerate all of my characters, right? So basically what I am doing is I am enumerating all my characters, and I'm creating a mapping from character to integer, right? So it will look like this. A will be given 1 for, just for example. Okay, so it won't work like this. So whatever characters that you have, so example, A will be given 0, B will be given 1, C will be given 2. So string to integer is enumerating characters into integers. Okay, I am also making a decoder which is integer to string. So it will be a reverse of whatever was there. So it is integer to character for I comma character in enumerate characters, right? So in the characters, I am making them integer to string. So I am going to create encode, which is my string to integer, and I am encoding each character for character in S, right? So S is my string. Okay, so I am making an encoder, which is encode. So what it is doing is for each character in my string, it is taking this string to integer, the mapping it is taking, and it is converting um, this string into a array of numbers. Okay, because I am array of integers, right? So string to integer, what it will do, it will create a mapping for all my characters which I printed there, right? Here, right? So all my characters, I had 75 unique characters, right? So string to integer, what it will do, for each character, it will assign one integer. And integer to string, what it will do, for each integer, it will convert it back to character. Okay, so my encode will be for every character in my string. I am doing string to integer for each character, right? So my encode will look like a very long list of all the integers in my whole whole corpus. So my whole corpus will be converted into a list of integers. And this decode, what it will do is it is going to join integer to string for each I in L. So in this list, right? So in this list, what it is going to do is, if for every integer, it is converting it back into a character, right? So it is a reverse mapping from integer to character, right? So if you print encode high there, it will print you numbers that represent high there. And if you print decode of whatever you have encoded of high there, you will see the high there back. Okay, let's do it in code. And let me know if you are done with the encoder and decoder, right? So if you have done, then just let me know in the chat box with done or yes. right? So what you did is you created a tokenizer. So first step हमने कल ही डिस्कस किया था, परसों डिस्कस किया था, right? Yeah, in the collab tokenization code will not be there, so that you will have to type in, है ना? तो I have put in the guidelines, so you will have to kind of like do some work. Okay. Okay, if you are experiencing some error, maybe indentation errors will be there. Other errors will not be there. Okay, so you need to keep in the indent right. Okay, so in the last one, if you are facing some error, maybe some of the errors you are facing because of the indentation. Other errors will not be there. Okay, maybe I can get the whole code for me so that I can show it step by step and run the code for you. The previous step was, yes. So the previous step was this. Okay, so for 3.1, you need to check how many unique characters are there. So you're making a list of character, which is a sorted list of all the characters that are there. So it's a set of all the characters, unique characters in this text, and you are sorting it using a sorted function. All right, so for high there, you will get something like this: 56, 57, 57, 1, 68, 56, 53, 66, 53, right? So you will get something like this for high there as a function. Okay, so after this, you need to design the encoder and decoder. So once you design the encoder and decoder part of it, you will be ready for the next step, which is to encode all text to tokens, right? So to encode all text to tokens, we will step 3.3. So in your collab, um, maybe I'm not sharing my collab. So yeah. So here you just need to yeah. So here you need to create unique characters. So if you print this, you will see something a result like this, and we are creating a mapping from. It is not. I am not ready. I have to run all of this, and then here if I run this, I print all the characters. So I have these many unique characters and 75 unique characters in my uh, corpus. Okay, and if you encode high there, you will encode high there as this, and if you print the decode of encode high there, you will get the high there back. Okay, after that, what we need to do is we need to kind of like create a vector of all of my words, of all of my characters. Okay, so you cannot train. Last time we said that, right? So we need to convert word into vectors, right? So we are going to import torch, which is a PyTorch library, and we are going to use the encoding. So we are going to encode all the text using the encode function and create a tensor of it. So basically tensor is kind of like it's a one very large vector of a single dimension. Okay, so right now it's a tensor of 13 lakh characters. So all my characters will be converted into one long list of all the characters, right? So next is what we are going to do is we are going to encode all of our text, right? So we encoded hi there. Here we are encoding all of our text so that our text is ready to be processed. right? So we said that we will train our transformer model on my on text. So the first step is to tokenize it. Here we are tokenizing it by encoding all of my text. I am doing a character level tokenization, so I am converting all characters. So H is converted as 56 here, I is converted as 57. So now I want to convert all of my text that is there like this, okay, into numbers. And now right now this is a string, right? So this is a string of this is the array of characters. So all the characters are written like this. Now I need something like this. I need to convert it into a list. Okay. So I'm importing torch, and from there I'm creating this data. Data is the encoded uh, tensor of all these integers. So now my data will look like this. Now this is what computer can understand, right? Computer cannot understand this. It was not able to understand this because words and characters computer cannot understand. But computer can very easily understand numbers. So we have converted everything into numbers. Okay, so quickly do this, and we will be ready for our next part. So we are now encoding the entire text data set and storing it into a torch.tensor. Because we will be working with vector, that's why we are using PyTorch library to convert it into a tensor. Okay, tensor is nothing but a very long vector of one dimension. So this vector will be of a dimension 13,34,646. Okay. So Sachin is asking, sir, are the number randomly assigned? So in ideal case, no, we want to assign random numbers, but right now we are not assigning random numbers here. Why? Because we so the how the numbers are assigned is where your token will be in this series. So this space is there. Space will be assigned 0, and this will be assigned 1, this will be assigned 2, this will be assigned 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and subsequently. So if you see H here, so H comes somewhere here, right? So this H is 56th in this position. So these are not random assignment. This is a series assignment of these tokens. Okay. So generally we don't do character level tokenization. We do something called byte pair encoding. Okay. So byte pair encoding is what learns which two characters sit together, and we kind of like classify them as tokens. But byte pair encoding will be out of scope of this masterclass, because that will again take one separate lecture for just explaining byte pair encoding. So we are not going to do dig dive into that. Um, Maybe I can go for intuition, but these are not randomly assigned. Okay, so Ayushi is asking, why do we need tensor instead of simple array? So we need to work on vectors, right? So um, later on, I told you that we can't work with tokens as just numbers. We need to have a vector representation of these tokens, that we need to know which two characters, we need to know the similarity between two characters, right? To understand the meaning of these characters. Yesterday we talked about what is vector. So king minus man plus woman equal to queen, right? So we need to also understand how they line. So if we are working with vectors, then we need to convert each of my character into tensor, right? Because we will be using the matrix multiplication of the tensor. So later on we will be using vector space. So tensors are what will represent our vectors. Okay. Okay, now, so we encoded all of our text to tokens. The next thing is we need to split the text into training and validation sets. Okay, why do we need that? Because in machine learning, you are training your data into, you are training a big neural network into, to learn the patterns in the data, right? So you do also need to split it into training and test set. So you will train on your data on some part of the data, and then you will test your data on some part of the data and see if your training is working fine or not. Okay, so generally we do a 80-20 split, but because we have a large corpus, हमारे पास 13 lakh characters हैं, right? So for 13 lakh characters, if I take 10% also of 13 lakh, that's almost around 13,000, right? So I can use 13K characters for test set. So I'm doing a 90-10 split. Okay, so we are splitting this for 90-10. Subhadeep is saying that we can also use pandas for mathematical calculation. Why tensor only? Because with pandas, we will not be able to do vector calculations, right? So tensors are representation of, tensor are like arrays of vectors. So we'll be able to work better with vectors. So here what we need to do is we need to split it to um, Niraj is saying we can perform tokenization using both NLTK and SPACY. We can perform tokenization with NLTK and SPACY, but that is more of a word level tokenizer, and that's a hard coded tokenization, right? So it's kind of like you are tokenizing by certain rules. It's a rule based tokenization. In general, we don't need rule based tokenization. We want to learn tokenization as well. So I wish I could talk about byte pair encoding, or maybe we can talk about byte pair encoding as well. So I will just give you an idea of that as well. Um, I think I have a PPT for that as well. So I will just quickly explain why do we need to do the tokenization ourselves. Okay, maybe that will be my. Just give me a second. And I think here. Okay, yes, I got it. Now I will just share that byte pair encoding part as well. Okay, so what you generally need to do is you need to learn tokenization also. So you need your model to kind of like learn how it should tokenize this. So what GPT-2 did was they used byte pair encoding. So byte pair encoding is learning how two characters are together in any language so that we can combine them to make one token. So let's say we take a example of this. So let's say you want to encode this word AAABD and you have only 4 characters in your vocabulary. So A, B, C, and D, right? So you want to learn how to tokenize this. You want to know how to chunk this up. So what you do is you kind of like look for pairs of 2 characters or 2 bytes which are together, which are more common together, right? So in this, I have AA and AA together. So I will do one thing, that I will assign one more vocab term Z that will represent this byte pair. Okay, so this will represent AA together. So I am basically compressing my vocabulary to ZABD, ZABAC, right? So because I introduce one more vocab term, one more token in my vocabulary, which encodes AA because they were together, right? Now I see that AB and AB are also together. So I will encode these two also together. And I will add one more vocab word, which is Y. Okay, so I will combine that to Y. So I will add this Y to my vocabulary, which will now represent AB. So my vocabulary is increased to Z and now Y. Now I see that ZY and ZY is also common here. So I will also encode them together. And I will make one more vocabulary term, which is X. So I encode XDXAC. So right now I'm learning from my corpus, how can I chunk this up? Okay. So now I cannot tokenize it further, right? So I have now 4 tokens. One, D is 1 token, A is 1 token, and C is 1 token. Okay. X is 1 token, D is 1 token, A is 1 token, and C is 1 token. So I only have like 4 tokens. Previously, I had these many words, right? So I need to, if this is like, let's say 10, so I need to make 10 tokens. So A. Now I'm compressing it to just 5 tokens, right? So when I decompress this, I will get this as my tokens. So B is 1 token, D is 1 token, A is one token and C is one token. And I represent them as numbers. So my numbers will be 1, 2, 3, 4, 5, 6, 7. 5 will be Z, which is AA. 6 will be Y, which is AB. And 7 will be X, which is AAAB. Okay. So generally we want to learn this. But right now, just for saving time as well as compute, we are not doing the byte-parent coding. We are doing a simplistic way of tokenizing by splitting them into integers. Okay, so we are just giving 1, 2, 3, 4 random integers. All right, so now I need to split it into training and validation set. So just quickly do this as well. You are kind of like dividing it into 90% training data, and the data will be from 0 to n, which is 90% of 13 lakh 36,456, and validation data will start from after 90% of it to the end. Okay, so we are doing this. All right, so perform this as well. Okay, what I can do now is maybe you don't need to write the code because that will take longer time. Maybe I share the code with you and explain it, right? So that would be a right way approach of doing this rather than me waiting for you for the code. Okay. So what you do with me is run each section of the code. Okay. So I'm sharing you my code of how I designed my large language model, and I need to run that code one by one. So maybe I can save you with the depth of okay. Okay, I'm sharing the wrong screen. Okay, yeah, maybe I'm sharing so I will share you my code. Okay, and I will explain you how it is working. So just give me 1 minute. So I'm going to share this link in everyone's group, and you can just kind of like go through the code and learn how it is working. Okay, rather than kind of like typing the code. All right, so um, we have reached here. So where we created our own tokenizer, and we created a tokenizer and it converted them into words, sorry, numbers. And after that, we converted them into a into a tensor for training. Okay. Now what we need to do is, if you are into the code, you can also run the code and make a copy of it and run. So that you are not hampering the whole code itself. Okay, so we need to split the data into training and validation set. So we kind of like just splitting it. So my data is now 90% data for training data and 10% data for the validation data. Okay. Now I need to feed the tokens to transformer, right? So next step was chunking it into tokens and now feeding the tokens to the transformer architecture. In the last class, I told that the transformer architecture, we only need the decoder part of it, right? Not the encoder. So this is the input embeddings, and I am feeding my tokens to my transformer architecture all in parallel. Okay, so let's say that I am feeding 8 tokens. Okay, so that will be my block size. So I will feed some number of tokens at certain time. So I am feeding 8 tokens at one time, and my training data will be from first token to block size plus 1, right? Why? Because I am you understood how the prediction happens, right? So prediction happens by randomly chunking my text from any part, right? So I will randomly chunk my text from any part and I ask it to predict the next token, right? This is what we learned in the last class. So you randomly chunk, you ask it to predict the next token, you randomly chunk from somewhere and you ask it to predict the next token, and then you randomly chunk and then you ask it to predict the next token. And this is how we are making this large neural network learn, right? So we did it with Taj Mahal example, that if you want to learn Taj Mahal is in Agra, you randomly chunk it from some part and you ask it to predict, and it will predict something wrong. And then you back propagate the error, and then you ask it to adjust its weights and biases. So if my input or my block size is 8, then my training size is 8 plus 1, 9, because I want to predict this new token, right? So that's why my training data size will be block size plus 1. Okay. So here, so my tensor uh, will be this. So my block size is 1. So my block size is 8. So it will start from here. So it will take first 8 characters from here, right? So 1, 2, 3, 4, 5, 6, 7, 8. It will take these first 8 characters. So this is what my block size will be. And my training data will include the 9th character as well. So it will have 24 also as a character, right? So it will be a tensor of 9 characters. 1, 2, 3, 4, 5, 6, 7, 8, 9. Why? Because if this is the input, we want to predict the next character, right? So this is how it works, right? Okay. So what are we trying to do? We are trying to make this neural network learn. So this is very small toy neural network, and I'm working with this toy neural network. What we are trying to do is we are trying to learn these weights of this neural network. Okay. How these weights will be learned? So if this is my initial characters like CHAPTER, and then there is space. If I have C as my token, then I'm trying to learn that H should be the next token. Okay. If I have H as the token, I'm trying to learn that A is the next token. If I have CHA as my tokens, I am trying to learn that T should be the next token. If CHAP are the tokens, that I'm trying to learn that T is the next token. And if CHAPT is the token, then I'm trying to learn that E is the token. And if CHAPTE is the input, then I'm trying to learn R as the token. Okay. So this is what I'm trying to do. So I will define my input and output. So my input will be training data from 0 to the block size, right? So here you can see, and my output is my training data 1 to block size plus 1, right? So if my input is 42, I am trying to predict 30, right? So because in this tensor, after 42, 30 is the next character, right? So I'm trying to predict the next character only. This is how I'm training the large language model, right? So this is what we saw in the last class, that ChatGPT only predicts the next token. It does nothing else. It is only predicting the next token in the sequence, right? So if my input is 42, I am predicting that 30 should be the next token. If my input is 42 and 30, then I'm predicting that 27 is the next token. Okay. So if my input is 42, 30, and 27, then I'm predicting that 1 should be the next token. If my input is 42, 30, 27, and 1, then I should predict that 35 is the next token. If my input is 42, 30, 27, 1, 35, then 23 should be the next token. And if I take 23 into input, then 30 should be the next token. Then I take 30 into input and 23 is the next token. Then I take 23 into input and 24 is the next token, right? So we are predicting this. So y will be one shifted value of this tensor. So I take this 8 values here, and y will be one shifted value of this tensor. That means that y will start from 30, 27, 1, 35, 23, 30, 23, and 24, right? So my context is x up to t plus 1. Um, so making t here, so 0, because t0 is, so making it from 0 plus 1, 1, so t1, and then t1 and t2, from 0 to 1, then so from 0 to 2, from 0 to 3, and y is t, right? So it is like, if it is 0, then t0 like 30. For 42 and 30, it should be t1, which is 27. For 42, 30, 27, it should be 1, right? So this is what we are doing. This is also only what we are doing in transformer architecture. We are only predicting the next token. So we want to predict the next token. That's why my input will look like this, and my output will be one shifted value of that. Okay. I'm going to pause to take some questions here. And can you please show step 4 once again? I have shared the new collab, so you will see all the steps in the new collab now. Okay, so in the new collab, you will be able to do all the steps. So I've shared the whole code because I don't want you to write the whole code. I just need to explain the whole code to you. What we will do is, what I need from you is need to make variation of this code. Okay. Okay, so some people are saying that there is no code after tokenization because that is a new file. So I have shared the new file as well. So you can use the new file for this now. Okay, so now what we need to do is, after we have done this, we need to train in 3 dimensions. Okay, maybe I should erase this. we need to train in 3 dimensions. What are these 3 dimensions of training? I will explain. So one, we need to, okay, step 5. Samiksha is saying, explain step 5. She did not understand that. Okay, step 5, maybe. Yeah, this. Okay, so we are feeding these tokens to transformer, right? So we want to feed these tokens to transformer parallelly. So we are feeding these 8 tokens right now, which we call as block size. Okay, so we can feed any number of tokens. That depends on how many GPUs do we have, right? So the more the compute power, the more tokens we can feed in parallel, right? So right now I'm starting with 8. My if my input is 8, then my output should be one more value after 8 tokens, right? Why? Because I am only predicting the next token. So if I have here, if I'm predicting, so my training data should be of 9 characters. My input will only be of 8 characters. Why 9 characters? Because I need to predict the next character also, right? So after this, what should be my next character that I am also predicting. So if my input is 42, my next output should be 30. And if I have these 8 characters as input, I also should have this ninth character because I'm predicting this character, right? So in this big tensor, after these 8 tokens, I am predicting this ninth token. So that's why I will keep that in my output, right? So my output will be one more character and one shifted character. So after 42, it should start, my output should start like this, right? So for 42, I'm predicting 30. For 42 and 30, I'm predicting 27 and so on. Okay. So I think that explains it. After this, we need to train in 3 dimensions. Okay. We can't just go like in series. Okay. So, yeah, by this, we are not able to understand the context. Okay. So Ayushi is saying that context is not being understood here. Right now, we are just inputting our, we are at a very, very small stage in designing our transformer architecture. That means that we are only in the input. Context will be understood here. Okay. We are not even reaching to this part. So right now we are just feeding it to transformer and asking it to predict the next token. Okay. So now after this, what we are doing is we are going to train in 3 dimensions of training. Okay. So I have shared the code, so you don't need to code with me. So if I'm going fast, I'm going fast because you can use the code that I have shared with you and can just work on the code, right? So you don't need to type the code. You just need to understand the code. Okay. So 3 dimensions of training, maybe I will explain this. So one is the time dimension, right? So in time dimension, each time we are predicting the new characters. So I have these 8 characters at input. So I am predicting this character at one time. Okay. So if I am at T0, I am predicting what should be my character at T1. If I have T0 and T1, I am predicting what should be my character at T2. If I am at T0, T1, and T2, I am predicting what should be my character at T3, right? So I am moving in time dimension like this, where I am predicting the next character. Okay. I also need to parallelize, right? This, if I go this way, it will take a longer time to train. And also it is not, it is not good to train, like it is good to leverage the GPUs because we can train parallelly. So I will also create one more dimension, which is the batch dimension. So I will train in batches. So these 8 characters I will randomly take from some different parts of my corpus. So 1, 2, 3, 4. If I have 4 different batches, then after K I am predicting U. Similarly, in the same time after W I am predicting right R. After W I am predicting H, and similarly in the same time I am after W I am predicting O. Okay, so I am making this one more dimension where parallelly I am training from 4 different parts of my corpus, right? So not only I am saying that, okay, after Kurukshe T should be the answer, like chunking it from here, randomly cutting it from here and asking it to predict. But I am also randomly cutting 4 times in my corpus. And then I can randomly cut it many times, depending on how many GPUs do I have, right? So randomly cutting my corpus from different parts, and this will be my batch dimension. Okay. So I work in batch dimension. That means that I also parallelly want to want to predict in it from 4 different places in my corpus. Okay. So instead of doing it only once and serially, I am doing it at 4 different places. I'm randomly cutting at 4 different places and asking it to predict the next character. And then there is one more dimension called channel dimension, which I will explain and explore later. Okay. So here at this code, what I'm doing here is I am going to, here what I'm doing is I am adding one more dimension, which is the block size. So I'm randomly, so my block size is 8. I'm randomly cutting my corpus from 4 different parts. So at one time, I'm training my transformer on 4 different parts of my corpus. Okay, so this will make my training faster. So I'm going to make a function which is to get the batch, and I'm splitting this and I'm using the split function. So what I'm doing is I am randomly splitting my data at 4 different intervals, right? At batch size, whatever be my batch size. Here it is 4. So I'm randomly taking one value of ix, which is randomly taking 4 different values from where I will cut my data. Okay, so my x will be a stack of data from that I to I plus block size value. Okay, and my y will be one shifted value of this I plus 1 and I plus block size plus 1. Okay, and then I will return x and y. So basically we are creating batch of 4 different batches where I will do the prediction. Okay, I have it explained here, right? So my tensor should look like this, right? So at one point I am training for parallelly for at 4 points. So I'm inputting these 8 characters. I'm inputting these 8 characters from random some other part of my corpus. I'm inputting this 8 characters from random some other part of my corpus, and then I'm inputting these 8 characters from random some other part of my corpus, right? So this is how the intuition of this is. So I'm randomly initializing 4 start points in my code from where I will chunk these 8 characters and train on these 8 characters. Okay, so to give the parallel property for this data. So here what I did was a batch size of 4 and my block size was 8, and I randomly split it in 4 different direct dimension, which is initialized by this batch size, and I take that as input. So my input will be a tensor of size 4, 8. Okay, so my tensor will look like this. So these are 8 characters from one random location, which is from 30 where this should have been there, and this is 8 character from one random location, this is 8 character from one random location, and this is 8 characters from one random location. And this is my target basically, to this 8 characters should predict this, right? So 33, after 33, 49 should be the prediction. After 33 and 39, 60 should be the prediction. After 33, 49 and 60, 57 should be the next character. After 33, 49, 60 and 57, 62 should be the next character, right? So this is how we are training. So my training is happening at 4 different parts of my corpus, and at 4 different parts, I'm predicting the next token that is there in the sequence. Okay. All right. So if I print the input to our transformer, it will, sorry, I should run this first. Then it will show the input to my transformer. So my transformer will get this tensor as input. So these are 4 different tensors that I will give as an input to my transformer. Okay. Okay. So this is how I created a random batch, and this is how it should look like. So we are achieving this. We are achieving a tensor of input, and we are achieving a tensor of output. So previously our input output pair, they look like it is. Yeah. So our input output pair, they look like this, right? So tensor of where this was the input and one shifted value was the output. Now uh it's we are training it on batch. So we have a 4 into 8 tensor, which is mapping to this 4 into 8 tensor, which is one shifted value of all the values. Okay. All right. So after this, what we will do is we are training in batches for parallelization. So for B in range batch size, for T in range batch size, this is the context and this is the output. We already have done this. Okay, now we talk about input embeddings, right? So in my last lecture, I talked that we cannot just work with these characters, right? These contextual information or any information about the other character, they are not related to each other. They are right now 90° to each other, right? So 33 and 49 have no relationship. So we don't know any relationship between these characters. Okay. So we need to also convert these characters into vectors to have some relationship between these two characters. Okay. So if you remember from my last lecture, we need to convert them into vectors. Okay. If I take in the PPT of the last lecture, then let me just open that. I think I can open a recent one from here as well. Okay, so from here, I can open the recent one, and I took this. Yeah, so we want to convert word into vectors, and yeah, so we want to convert it into some representation which has some context about the characters. So we are trying to understand how these characters are occurring together by this word embedding. Okay, so we want to implement this word embedding. That means that we want to convert word into vectors which have some information about other words. Or in our case, we want our characters to convert into vectors which have some information about other characters. Okay. So what we will do is we will import Torch and we will import neural networks from Torch to learn to integrate neural networks. And from torch.nn, we are importing functional as f. And I will just tell the use of all this. So basically, we are creating a bigram model class. We are kind of like learning how two characters they occur together in my corpus. This is one way of converting word into vectors. Generally, we want to convert vectors into dense vectors. This is sparse way of converting vectors. That is that we are creating sparse vectors. We are only learning how two characters are together in my corpus, right? How many times they come together in my corpus, and what is the probability that one character will come after these many characters have already occurred. Okay, so this is what we are using as embeddings. So our vectors will look like um, a vector of vocab size into vocab size. So this will be my embedding table, which will look like, so which will map each character to other characters. I will just show how it works and how it should look like. Mm, yeah. So basically, what I'm doing is I am creating an embedding table, which is of vocab size into vocab size, which is this table similar to what I explained in my last class, which is okay. Wait. Co-occurrence of these words. Okay, so we are in 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 Y, we will have all the characters in my corpus. In X, we will also have all the characters in my corpus. And we are kind of like seeing how many times these two characters have come together with each other. Okay, and we are using this long vector as representation of that character. Okay, maybe I can draw it in the PPT and then maybe explain this better. Input embeddings. Yes. So, so action. Okay. What we are trying to achieve is we have our characters A, B, C, D, and all, right? So up to so 75 characters. And we also have, like, we are trying to map them with other characters, and we are trying to see a relationship between these two characters to know how these two characters relate with each other. Okay, so it will be us up to 75. So this vector conversion we are doing by term frequency and inverse document frequency here. How many times A and A have occurred together? So there will be some number like 3. How many times A and B have occurred together? So that, let's say that in my corpus it occurred 17 times. Okay, I am taking very small numbers, but it should have occurred more than this. How many times A and C have occurred together? So let's say 23 times. How many times A and D have occurred together? So let's say 14 times. How many times A and E have occurred together? So let's say 29 times. Okay, so I am representing A as not just one integer now. So previously I represented A with 33, let's say. So now my representation of A will change to a 75 dimension vector, which also have understanding about other characters of my corpus, right? So I'm changing it from one integer to a vector of 75 dimension, which now has context about other characters also in my corpus, right? So this A will have now more meaning. It will now understand which other characters it sits with in this corpus, right? So previously A and B had no meaning, right? So A as 33 and B as 34 had no meaning, had no relation with each other. Now, if I convert them into vectors like these, how many times B and A have occurred together? So let's say 20 times. How many times B and B have occurred together? So let's say 14 times. How many times B and C have occurred together? So let's say 29 times. How many times B and D have occurred together? So let's say 31 times. So now I am converting my words into my tokens into something which have now relationship between each other. Now A knows that it occurs with B 17 times, right? So instead of them being perpendicular, A or B, now they will have some similarity. These vectors will now not be perpendicular, but they must be lying in some direction if A and B occur together more in this vector space, right? So they have some meaning now with each other. Okay, this is what I'm doing here. So I am converting my word into vector. So I'm doing it with diagram language model. You can do it with word to vec algorithm. You can do it with other vector representation of words. But the simplest way is to use them the sparse vector, right? So you can convert them into dense vector, and then you can train a neural network to learn the weights of this dense vector. There are many ways to convert word into vectors, but we are simply doing it with this. Now, here, each character is now embedded to a vector of vocab size, and each vector now stores the scores for the next possible character. So basically what this vector represents is after H, what should be the next word, next token, right? So this has some understanding of the text now. So after H, T should be the next token. This is what these vectors store, right? So after H, because the score of T is high, so after H, T should be the next token. This is all what it is representing, right? So now from each token being independent, we have now tokens which are dependent with each other. They have understanding of how they occur in this in this text. Okay. Now I will define a forward function which will forward my tokens, my logits. So these logits are what I'm going to do is we are going to make a token embedding table the index of that character. So if I want to have the value of A now I will go into this token embedding table and take all the values of A from from this index, right? So if I want A now, so I will take in this 75 dimension long vector um, instead of just 33, which was the value of A as an integer. Okay. If target is none, then loss is none. I'm initializing the initial condition. Otherwise, I have this batch, time, and channel dimension, which is the shape of my logits. And this logits, if I see them, then they should be batch into time dimension, batch multiplied by time dimension, and they should be a tensor of a channel dimension one. And the targets, they will be just in batch and time dimension. So basically, after this 75 dimension long vector, my target is just B, which is this batch into time, which is, let's say, 34. Okay, so if I want to predict AB, so after seeing this 75 dimension vector, I'm not, the target will not be a vector. It will just be some character, which is 34, right? And this loss that I'm propagating is this cross entropy loss. So in my neural network, I will back propagate this loss in order to adjust its weights and biases in order to learn what should be the next token. Okay. So I will just run this, and I have a forward class which forward propagates these weights. And here I also have this generate function. So this generate function, what it will do is it will generate some new tokens. Okay, so what it is doing is it is in range of these new tokens. It is calculating, it is taking logits, and it is taking loss, and from the index in from the index in the table of vocab size by vocab size, means from the embedding, it is going to predict the next token, right? So from IDX, it is going to predict the next token, and it is going to take that next token and going to concatenate that next token. Okay, and then it should return the index of that next token. So it is generating new tokens, and it should generate these new tokens by calculating the loss, and it is going to softmax that loss and select the best next token that needs to be generated, and it will generate that. Okay, so if you take in input xb and yb, and you take in logits xb into it and loss um, and yb as the output, and then if you print the logits of the shape, then you will see that it will be a torch of size 32, because 4 into 8 is 32, and it will be a 75 long vector, right? And if you print the loss is 4.4978, and this is the backward loss, right? So if you print the next 100 tokens based on just how one token sit with each other, it will print something very gibberish like this. Okay, so it doesn't make any sense, right? So what it is doing is, what we are doing right now is we are converting word into vectors, and these vectors are sparse vectors. That means that they only have understanding of how these two tokens sit with each other. Okay, and then we are doing a forward pass of these vectors into this token embedding table. So we are just multiplying these characters which we had with their respective meaning, with their respective vector. And with these vectors, we are calculating the logit and loss, and we are back propagating that loss, and we are predicting that what should be the next character. So we are training we are training a bigram model, which is of size vocab size, and we are just printing the next 100 tokens, and it will print something like this. This does not have any understanding, right? So this is just what we get after doing word embedding, which is just the first phase of our transform architecture, right? So we have done up to here only. So we tokenize the words into different tokens, which were some number. And now these numbers are now represented by a vector which had some understanding about other tokens, right? So, and this understanding about other tokens, we feed into input embeddings. And after, when we are generating next token from this was generating something very random like this. Okay. We also need to optimize the loss. So we are creating a PyTorch optimizer. We use Atom optimizer for loss because it is good. So you can check on Atom optimizer. And Atom optimizer is most widely used computational efficient optimizer in deep learning that updates network weights iteratively based on training data. So we are using Atom optimizer to update my weights for optimizing my weights. Okay, so it is the learning rate should be uh, of 10 to the power minus 3 because it is we don't want to kind of like overtrain or undertrain. Okay. Then for practical purpose, we want to increase the batch size. So we started working with 8. So I'm now increasing it to 32. And yeah, so for 32, I'm going to get the batch which I want to train, which is the training data. And I'm going to take in the logits XB and YB, and I'm going to train it on loss. And I am going to back propagate that loss into my neural network, and I'm optimizing it with my optimizer. Okay. So once you kind of like start doing that, so you will see that the loss is 3.77. Okay. And with after optimizing this, if you print the first 500 tokens, you will see that there is some structure becoming of some structure coming into this text that it is generating, right? So previously it was generating it some randomly like this. Now it is generating some text which is in verse form, right? So my Mahabharata, if you see, it is also in kind of like these sentences which are randomly cut from which terminate randomly, like poems terminate randomly, right? So they are not long sentences, they are short sentences. And now we are seeing that we are able to generate something like a poem, right? So it is a array of sentences, but it is not still legible. We are not able to read it because there is no context in these two in these two characters. So it only knows which characters sit with what, and that's why it is predicting this. So we want to move to self-attention, and which we discussed last time, right? So we don't know if my input, what should be my input be looking at in order to predict the next character. Right now, it is just predicting the next character based on the scores that it has given. So if H sits with B more, then maybe B should be the next character, right? And this is what I'm getting. So after exclamation, I am getting S. So S should be this pair should be more time in my corpus. After 0, it is predicting X. After X, it is A. So it just is predicting the next token based on how many times XA has come in my corpus, right? It doesn't have any sense in it. So we want to have sense in the words, and that's why we will do attention. And we will move on to our next section of transform architecture, which is the attention module, right? So here in the transform architecture, we have now output input embeddings. We are feeding everything in characters. So positional encoding I am skipping, but we should also have positional encoding. That means that we should know which character came where. But for character level tokenization, we don't need this. So we are going straight forward to self attention and mask multi-head attention. How it works and how can we kind of like implement that. Okay, so the mathematical trick in self-attention and how self-attention works is I will just go to self-attention. Okay, so self-attention. Code. Okay, we want these tokens to communicate with each other. Right now, they are not communicating with each other. They are only predicting the next token based on how many times it has seen prior, right? So self-attention says that if I want to predict VAS based on A, what should A be paying attention to in order to predict correctly, right? So it was only paying attention to the previous word right now. Okay, so it was saying that how many times I have seen D, then A should be the next answer. How many times I have seen A and V together, so V should be the next answer. It was only predicting it on the basis of word frequency, how many times these two are occurring with each other. But with self-attention, we also want it to predict which which character it should pay attention to, so that V should be the next possible answer, right? So it should be able to predict V by A looking at D, N, A, and P. It should pay attention to P, A, N, and D, and then should predict V, not just looking at the last character, right? So self-attention was that only, where if you want to predict the elephant could not fit in the car because it was too big. So if you want to know the meaning of it here, you want to look at elephant and big, right? So that's what we are achieving with self-attention, right? So the token at any point should not communicate with the future tokens. It should only communicate with the previous tokens. Okay. So very simple way of communicating with previous token is taking their word vector. Okay. Each one of their word vector and taking the average of all the vectors there in order to predict the next token. Okay. Very simple way is to take the average of all the vectors and predict the next token. So, the average can be taken by taking the mean of all the previous vectors and predicting the next token on the base of that. Okay, so this is what we will do with code as well. So here what we are doing is we are initializing a, a, a triangular tensor or a triangular matrix which has zeros on the upper low, so that if I have one, if I have one if I have like P, then it should only look at P itself in order to predict next. If I have PA, then A should only be able to look at P and not at the other words ahead, right? So what we are doing is we are basically masking up uh, our uh, our data, right? So in order to predict V, A should look at PA, N, and D, right? So we are doing this by masking the future values. So P should only be focusing on P in order to predict A. A should be focusing on P in order to predict N. N should be focusing on P and A in order to predict D. And D should be focusing on P, A, N in order to predict A, and so on, right? So how to do that with code is I am going to make a matrix A, which is a triangular matrix where if there is P, then P should only look at P, other values should be 0. If I have P and A, then P and A should be able to look at P but not at D. If I have P, A, and N, then N should be able to look at all these things. Okay, so this is just an example of how we can do this, and I am going to make A as sum of A. That means that I am going to make a tensor B, and C will be a tensor A multiplied by B, where I am normalizing these values, right? So one way of communicating with these characters is also to take in the average of the tensor. So I'm making this tensor and I'm making the average of this tensor up to 1. So like 0.5 and 0.5. So if I have PA, then A should have half of the value of A and half of the value of P, right? So it should know about P as well. Yeah, so maybe I can explain it with this. So consider that there is a 75 dimension long tensor, but this is now just a 2-dimension long tensor. And uh, what I'm doing is I'm converting this input into a tensor where this input also have, so let's say P is this and A is this in my input. Now my A changes to have some information about P as well, right? So I'm dividing P by 2 and adding it to A by dividing A by 2 as well, right? So this is just communicating these two by taking the average. Okay, so we could have also taken the average, but in reality, what we need to do is which comes here. So basically, we convert it into a tensor of a triangular matrix, and then we kind of like normalize it. And then one more idea of doing that is by initializing it with infinity. Okay. Wait, I will just explain it somewhere here. Yeah. So this is just an example of how what we are trying to achieve. We are trying to achieve is if I have uh, one character, whom should it look in my in my input to predict the next token, right? So if I have P should look at P only because it cannot look previously to any character. If I have A, then A should look at A only and not P, right? So I'm trying to achieve this value. The higher the value of this, that token I only need in order to predict the next token, right? So here I need to pay attention to A in order to predict the next token. Here I need to pay attention on N in order to predict the next token and not P and A. Here I need to pay attention to P in order to predict the next token, right? So I am taking Pandavas as example. So P A N D A V A S. So in here P should pay attention to P. Here A should pay attention to A. Here N should pay attention to N. But D should pay attention to P in order to predict the next token, right? And here it should pay attention to some other way. So I'm going to find these values on of the words that I should pay more attention to. Okay, so what I do is I create the key vector, I create the query vector, and I create the value vector. This is what I taught in the last class, right? So each vector is converted into query where to key vector. So I am trying to find out which vector I need to pay more attention to in order to predict the next token, right? So this weight I am trying to learn. So this is what I will do and learn in this matrix. So I will create these three weight matrix, which is query, key, and value matrix, and I will calculate the weight of this query and key vector, and I will take this vector, this value, and I multiply this with a value vector to in order to know which token I need to communicate in order to predict the next token. So my table will look like this. This will tell me which character I need to pay more attention to in order to predict the next character. Okay. Uh, I also will do layer normalization, and so what I'm doing here is I am going to normalize my weights. So I'm using here the mean normalization. So this is one of the common normalization here. So layer normalization I'm going to do here. So I'm normalizing all the weights in here, and finally, if I run this code. So this is the whole code. So if I run this code where I have batch size of 16, so I am randomly cutting it from 16 sentences, block size of 32. At one point, I am training it on 32. My maximum iterations are 5,000 and my evaluation iteration is 100. My learning rate is 10 to the power minus 3, and I'm using CUDA. That means that I'm using GPUs if GPUs are available, otherwise CPUs. Evaluation intervals are iterations are 200. Number of embeddings are 64. Number of head and number of input layer are 4. Dropout is 0.0, right? So these are some hyperparameters which I explained. So dropout is you need to drop some weights in order to make your neural network efficient. So this is also one of the parameter that we need. Number of layers, number of heads is we need to also extract multiple information. So we do a multi-head attention. That means that we need to extract more than one relationship of one character with other character. So we use like masked multi-head attention. That means that we use multiple attention layers, not just one. So here in our case, we are using 4 multiple attention layers. If you see my output here, then it is training my neural network. So on step 0, my training loss was 4.5 and my validation loss was 4.54. So it is training for 5,000 steps. and it is right now learning the how each character is associated with other character. It is also learning the attention mechanism between each characters and how what it should pay more attention to in order to predict the next token. And it is mapping these to all the 75 tokens that are there, right? I will show you how it is working in the code. So yeah, so here you open the text and you make it a sorted list, and here you make the tokenizer. You are converting it into the training and test split. You are loading each batch where you are making y1 shifted value of the batch, and then you are estimating the loss here. So this is important, where you are defining the one head of self-attention, where you are converting each vector into a query key and value vector, and you are selecting the you are you are understanding the context of each vector by multiplying the query and key vector and finding out which characters it should pay attention to in order to predict the next token, right? You are also doing dropout, which is that you are dropping out some weights in this neural network. This neural network is a linear neural network of size n embeddings. So in my case, n embeddings are 64 up to head size. My head size is 4 here. Yeah, so number of head is 4, and so I'm making neural network from 64 to 4, and the query is also from 64 to 4. My value vector is also from number of embeddings to head size. And here in forward, what I'm going to do is I am going to calculate weights of query and key vector. These weights are masked weights because I want to not look forward um, in my layer. So that's why I am introducing minus infinity in order to block the future tokens, right? So I do a softmax and I select the value of the largest weight, and which is what I'm doing to calculate the value of v. So v is the value of value vector of x. So my x is now converted into the query and key vector and weight multiplication of that, and my output will be weights into this value vector, right? So these weights are query and key vector multiplied together. Finally, what I will do is I will do a masked multi-head attention, and this masked multi-head attention will convert this into different attention heads, and then I'm learning this different relationships between each other. And my final output, which you will see, is that after 5,000 steps, it will start generating the next tokens. Okay. All right. So we need questions. Questions is one is what is the meaning of seed here? So seed is basically for my answer and your answer to be same, right? So otherwise, if I don't keep seed, it will randomly cut it from one part or other part. Uh, Finally, yeah, so I will just wait for my transform architecture to train, and I will just show you the result. So you can also do the same with the code as well. And you will see that there is we will generate some text based on the transform architecture. All right. So by training this large neural network, we are training it on 5,000 steps, and we are predicting what should be the next tokens after these steps. So let me just train it. If you have questions, you can ask it in the group, and I will be happy to answer. So Veena had a question which I am not able to now access. So Frickson says that what does loss mean? So loss is uh, loss is y predicted minus y actual, right? So let's say that after A, B should have come, but my model, let's say, predicted C. So the loss is the here we take in cross entropy loss, which is negative log likelihood of y. So minus y into log of y. But loss is basically, if I talk about intuition, then I already know what is my next character, right? But if my model is predicting something else, then my y prediction minus the y actual would be my loss, which I back propagate it into this neural network. Okay. Veena is saying, how does industry convert unstructured data into structured data set with proper features? What tools and pre-processing pipelines are typically used in companies? Um, there are many different ways to do that. You need to have kind of like a pre-processing steps involved, and each industry, depending on the use case, they design their own pre-processing pipelines. This is kind of like a very intensive process which involves a lot of human labor as well, and some of the things are automated. You said that if how did I decide it should be 500? Sashini is asking. So why 500, 5,000 is because I am my batch size. It depends on what my batch size is. Okay, so here my batch size is 16 and my block size is 32. So at one point of time, I am doing 16 into 32 calculations, right? So if I take the calculator and so this is a hyperparameter that we tune. You can tune this to many iterations as well. So if I say that 5,000 and I multiply it with 16 and I multiply it with 32, then it's 25 lakhs, right? So I have 13 lakh characters. I am training it on 25 lakh characters in 5,000 iterations, which should be enough to cover all the characters, right? So I need to tune this hyperparameter. So your task will be um, to make these values, make the value change and see if the loss is kind of like converging. So right now my loss is converging to 1.54 after 4,999 steps. And this is how my transform architecture is generating text, right? So now it is saying Dakshmaya raises behold in Hoppen Komen and all. And it is kind of like converting it into a beautiful Mahabharata kind of like text, which is not a very good, but still like readable. It is English. From this, so we started something like this, which was very random, and we are achieving something which is now legible by using the attention mechanism, training it on data, and training it with transformer architecture. And like after that, it kind of like starts to understand the context of the words and then start to generate better words. If we have like bigger corpus and if we have like um, more data to train on, it will improve better. And in the next section, we will see that how can we make it more better and how can we make this text better than what it has generated now by just changing some of the things in my transformer architecture, right? So right now what I was doing, I was converting them into query key and value vector to understand the self-attention between them. Then I was doing a feed forward layer. So my feed forward layer is a ReLU, which I mentioned last time. It is just to impart stability. And then after that, I am using this transformer block, which is communication followed by computation. So it is taking in the multi-head attention, and then it is doing the feed forward of that weights, and then it is normalizing these weights. And after that, it is using generation to generate this, right? So in the next class, what we will see is we will see the variation of transformer architecture and how can we use them to create our own AI agents. So next class will be not that much code heavy. This one was because we needed to understand how transformer work in order to make our own agents in the next class. So see you in the next class. If you have questions, you can ask it in the chat box. Otherwise, handing it over to CSR box team for wrapping it up. Okay, so
All right, thank you.
yeah, I will just have one question attend by Subhadeep. So Subhadeep is saying that he's currently working in a team project in healthcare. Can I make required AI model for our project after this course? Maybe you will need to fine tune your model and you will not be able to design it from scratch. If you have like GPUs and if you have a better bigger compute, maybe you will be able to do that. But in the next class, we will be making an agentic AI where we will be using pre-trained model to create our model. So that will be a good class for you to take to design this. So in the next class, because we just are designing it with limited compute power, in the next class we are using to use the pre-trained models, and we will use them to create agents for ourselves, which will do whatever that you want to do with those large language models. So next class will be more a practical application. Today class was more about how can we design our own transformer. So this is more about like which you will get questions on in your interviews if you go for large language model companies. The next class will be how can you implement them for your own use case. How can you design agents that can do certain kind of tasks? Yeah. Okay. Over to you, Anelia. If I get questions, maybe I will answer them by typing.
All right. Thank you so much, Amit. Um, so can you please close your screen too?
Yeah.
All right. Thank you, Amit. All right. So my dear students, I hope that all of you have learned how to create your own tiny language models. So please, you have received the links and other, we have shared the kind of things in your WhatsApp group also. So you can, so please watch the video again if you want, and you can just try it at home. And so I just want to make a couple of other, and in case if you have any doubts, you can also in the meantime you can chat with Amit, so he'll be replying it. So meantime, let me just make you a quick announcement once again. So guys, we know that you are facing some issues with the domain ID and password which you have received. So I request everyone, if you are facing any issues with the domain IDs and the password, and if you're not able to log in, or if you are facing any kind of login issues, please use your personal ID to complete the deliverables, complete the assignments. Okay. So it will not affect your certificates or other things. So, but in case if you can access the domain ID and password, if you are able to log into the mail, CSR box mailbox, then you please complete it with the domain ID and password. In case if you are not if you are facing any issues, only if you are facing any kind of issues, if you are facing any kind of troubles in login with the domain ID and password, please use your own personal ID. Okay, so by the time we will rectify the issues, and we will have another session for the IBM cloud, right? And also please note that those students who have not used or activated the domain ID, we will be canceling whatever we have sent to you, so you'll not be able to access it. So please, if you are working as a team, or if you're joining individually, or if your friends are a part of this PBL, we request all of you to at least try to log into the domain email box, and try to see whether you are able to log in or not, else we will be canceling it. Okay, and if you are able to log in to this domain ID, please complete the deliverable using the domain ID and password, right? Then again, I just want to inform you guys, domain ID and password is only to log into the domain mailbox. So this, we have shared the link that mail.sbcsrbox.com. So this is a mailbox, CSR box mailbox. So the domain ID and password is only to log into this account. Okay, some of you are trying to log into the IBM skills build, you're using the same password here, right? When you try to register, in the IBM skills build platform, you have to create a separate or a different password, which at least it requires a 10 characters of length. Okay, so we request all of you to create a separate password for the IBM skills build. So we have sent you the link in your in your email. We have sent all the links in the WhatsApp groups. Okay, so I request all of you to please go through the WhatsApp messages, please go through a mail. We have attached, we have given the documents, PPT documents and everything. So we request all of you to please go briefly go through the student resources. At least everything has been shared in the group, so please go through these documents, and it is very easy for you to complete the course. Okay, or it is very easy for you to navigate through the documents, and you will understand how to do this process. It is very easy. In case if you are still facing any issues, we will definitely have another sessions, or we will share you some video to help you in this regard, right? Then again, we will be having our third masterclass on 20th February at 5 to 7 p.m. So, like Amit said, we'll be having a practical application of the session. So please be ready for that one, right? And I will be sharing you the submission link for the second activity today, so you can submit it by tomorrow, right? And this is how the email look likes. And please check your inbox as well as your spam, spam folder, because sometimes this mail info at Caesar box is our mail from which we are sending the details, and so it might reach in your spam folder. So please you request everyone to check your inbox as well as your spam folder to see whether you have received the mail or not, right? And if you have any other doubts, please use the query forms. And uh, we are working hard, working overtime to respond to your queries. And I am sure that we have almost responded to almost everybody's queries. So even though it may take some time, like that, we are getting a lot of queries with regard to domain ID and password. And so we are telling again like that it may take some time, but we will be resolving all the issues, and we will send you the domain IDs and password, right? So we don't need to worry about that you are not getting it or you will not be sending like that. We will send you all the domain IDs and password in the meantime, right? All right, guys. So now it's time for you to punch your attendance. I kindly request all of you to mark your attendance, right? So we'll see you day after tomorrow for the final masterclass. So till then, we are signing off. Thank you. Thank you so much for joining. Bye.